Precalculus. We are in a new chapter. So, chapter 13. This chapter is called Combinatorics and Probability. Combinatorics is basically how many different ways can you combine things? How many different ways can you arrange things? Can you mix stuff together? How many different, stuff like that. Last year, I took a whole course in combinatorics, and we got into stuff like come up with a formula to represent how many different ways you can have a little string of some unknown number n of zeros and ones, and how many different ways for, let's just say n is 12. How many different ways can you arrange 12 zeros and ones such that you never have two zeros next to each other? And some stuff like that. We won't be getting into stuff like that. That's that's taking it to a different level. But this first lesson just kind of introduces some of the idea. And so this is lesson, we're in chapter 13, lesson 13.1. And I believe the lesson is called Permutations and Combinations. And combinations. A permutation is essentially how many ways can you arrange things. And then a combination is how many different groups of things can you form. That'll make more sense in a moment. But one thing that we want to determine first is the difference between independent events and dependent events. So independent versus dependent. In independent events, basically, one decision does not affect the other. We can put it that way. One decision does not affect the other. And usually what we mean here is it might be something like numbers that are used, digits that are used in a code where you are allowed to repeat. That would be independent. So in other words, it's like, oh, just because we used a 5 in the code does not mean we're not allowed to use a 5 again. We can still use a 5 again, right? So it'd be kind of like rolling a die is independent. Let's say you rolled it and you roll a 3. So what are the options for what can come up next? Well, a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Any of the 6 things can come up. Just because you rolled a 3, it does not affect what you have as options for what you will roll next. Or it might be something like you're at a restaurant and they hand you an appetizer menu and then a dinner menu and then a dessert menu. And the appetizer menu, it isn't like independent events would be like that because you can choose anything for the appetizer and then you can choose anything for the dinner and then you can choose anything for the dessert. It isn't like, oh, well, based on your appetizer choice, you only have these choices now for dinner. Okay, that would be dependent. Independent, the first choice does not affect the second choice. Okay? The first decision, the first outcome does not affect the others. I'll say the one decision does not affect the others. Okay? So when that's the case, what we use is what's called the basic counting principle. And how that works is this: number of choices times number of choices, etc. However many choices there are, you just multiply the number of choices to get the total number of possible outcomes. So an example there might look like this. Let's just say you have how many different combinations, how many different combinations kind of works there, but I don't want to confuse it with the combinations that we'll be dealing with in a moment. How many different outfits could be formed out of 3 shirts, 4 pants, and 2 pair of shoes? Okay. Well, we're not told that, oh, well, if you choose this shirt, then that affects the choice of which pants you can go. And we're assuming that you're the person that you're forming an outfit of 1 shirt, 1 pair of pants, and 1 pair of shoes. Okay. So this is independent. So we just multiply the number of options. So it would be, oops. So it would be 3 times 4 times 2. Let's see, 3 times 4 is 12, times 2 is 24. So 24 outfits. Basic counting principle, multiply the number of choices when the choices are independent. Let's do one more example that has maybe a few constraints on it. Let's say how many different codes can be formed if the pattern is letter, number, letter, number, letter, and numbers may not be repeated. Okay. So here it kind of affects it, but we can just still look at how many different choices we have. So for the letter, how many choices do we have for that first letter? 26. How many choices do we have for the first number? For the first digit? So I'll say I should clarify that the numbers are single digits. Number is single digit 0 through 9. Okay. So 0 through 9, then there are 10 options, and then another 26 letters to pick from. But now there are only 9 digits to pick from because whatever digit came first, we're not allowed to reuse it. And then another 26 letters. 1, 2, 3, 4, 5. Yep. So we multiply these out. So 26 times 10 times 26 times 9 times 26. And we get 1,581,840 different codes. Hopefully that makes sense. The next, let's move on to dependent. So here we have like each decision. Accidentally repeated that E, sorry. Each decision removes one option. So we can start out viewing this as if it's the basic counting principle, but there's a slight tweak. So let's just say, so it'd be like this. This is, well, let's put it like this. How many ways How many ways can you arrange a quarter, dime, nickel, and penny? Now, if we start out viewing it like the basic counting principle, for the coin that goes first, how many choices do you have? You have 4 choices. And then for the coin that goes second, how many choices are left? There are 3 choices now. And then the coin that goes third, now there are 2 choices, and the whatever coin is left, there's only one choice, one coin that's left. So what is that 4 times 3 times 2 times 1? Well, what is that? We can represent that as 4 factorial. So permutations end up being something that uses factorial. And so we can notate it like this. Notation. We're going to notate like number of permutations of n items taken n at a time. And that is just n factorial. So that would be like the problem that we just did. The problem that we just did. That would be like that. So that would be like permutations of 4 items taken 4 at a time. Meaning there are 4 items to pick from, and we're using all 4 in our arrangement. That is 4 factorial, which is what? 4 times 3 is 12. That's 24. Yeah. Okay. Well, we also can have like this. We also can have number of permutations of n items taken r at a time. So that would be like, let's just say you have 12 cups and they're each different, and you want to look at how many different ways can you arrange those 12 cups. Sorry, you have 12 different cups to pick from, but you're only arranging with 5 of them. Okay? So we have 5 items that we're actually arranging. Okay? Well, what that looks like is it looks like you start out with the 12. In this case, I'm saying we have a total of 12 items. And you look at how many different ways can you arrange 12 items. But then, because we're actually only using 5, for each arrangement that we pick, we don't care about the arrangement of the 7 items that we're not using. So what we do is when we don't care about stuff in this kind of a context, we divide by that because multiplying is what happens when you're adding options. Dividing is what happens when you are removing options, basically. And so what we need to do here is we need to divide by the number of items that we're not using. How many items are we not using? N minus r. And how many ways can you arrange those items you're not using? Factorial. So let's do an example with that. Okay. That would be like out of 12 different cups, how many ways? I'll say how many arrangements of 5 can you create? Okay, so this is a permutations of n items taken r at a time. So this is permutations of 12 objects taken 5 at a time. And so that's going to be 12 factorial divided by 7 factorial. Oops, 12 factorial divided by 7 factorial. And, well, 12 factorial is what? 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. Well, what's the 7 times 6 times 5 times 4 part? But that's 7 factorial. So this becomes 12 times 9 times 8 times, and that's it. Because the times 7 times 6 times 5 times 4, I'll tell you what, Let me write it like this. It'll make it clear. That's 12 times 9 times 8 times 7 times 6 times 5 times 4. That's 7 factorial over 7 factorial. So what are you left with? 12 times 9 times 8 times 1, right? 12 factorial over 7 factorial. 12 times 9 times... Oh, it must be like, what's with all the... I'm sorry. 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 factorial. There we go. I don't know what happened to my counting down from 12 skills. 12, 11, 10, 9, 8. So that's what's going on. Now notice it's the same thing as if you use the basic counting principle up here in the top left, where you just said, okay, for the first spot, how many options do I have? I have 12. Now for the spot 2, how many options do I have? I have 11. Spot 3, I have 10 choices. Spot 4, I have 9 choices. Spot 5, I have 8 choices. And fill it up like that. So you might be like, why don't we just use the basic counting principle always? Some of it is compactness of communicating what we're doing. And then some of it is when you get to bigger numbers, it can just become cumbersome. So 12 times 11 times 10 times 9 times 8, that gives us 95,040. 95,040. If you can't tell, permutations get big real quick. Real quick. Yeah. It's one of the fastest increasing because, well, anyway. Let's say, for example, you have a deck of cards, 52 cards, right? And if you took that deck of 52 cards and you shuffled it, rearranged a bit, shuffled it, rearranged a bit, shuffled it, made sure it's shuffled up pretty good. The number of different ways that you can possibly arrange a deck of cards is 52 factorial. 52 times 51 times 50 times 49 times 48 times 47. That is an insanely large number. Such a large number, if you had one deck for each different way you can arrange a standard deck of playing cards. I took the volume of a deck of playing cards one time, and I calculated out what the volume would be if you had one for each different arrangement. And the volume of the deck of cards, if you had one for each different way that you could arrange a deck of cards, is approximately the volume of 26,000 Milky Way galaxies. I'm not talking about the Earth. I'm not talking about our solar system. I'm talking about our entire galaxy and like 26,000 of them. Another way of putting how big of a number 52 factorial is. So to put in context how big the number 1 trillion is, if you started counting every second from the time God created the universe, every second, you'd be up to approximately 0.4 seconds now. Sorry, 0.4 trillion. You'd be at approximately 0.4 trillion. So 1 trillion is a crazy big number. If you took a deck of cards and you, let's see, what was that? And you were shuffling 1,000 of them per second. So, new deck. Yeah, 1,000 permutations, 1,000 permutations, 1,000 permutations, 1,000 permutations. I forget the exact number, but it's something in the range of like 5 trillion times a billion times a billion times a million years is how long it would take you to get all of the different permutations covered. So, yeah. Each time you shuffle a deck of cards well, most likely you are the only person in the history of the world who has ever shuffled a deck to that exact arrangement. I'll just let you chew on that as you would like to. Okay, so that's permutations. Let's move on to combinations. So combinations. Well, I'll go on to a new page here. This is still kind of over here. Combinations. We can say this. It's permutations where we don't care about the order. So all we care is that the items are together. We don't care about what order they're in. Okay? So our notation here is two different ways. This textbook does more of a combinations of n objects taken r at a time. Most commonly in other places, like all of my different other classes, is use this notation. Combinations of n items taken r at a time, or it's oftentimes also put n choose r. You have n items, you choose r of them. Okay? And the formula there is, well, we start out with arranging, in a sense, arranging all the items, but then we don't care about the arrangements of the items that we didn't choose, but then we also don't care about the arrangement of the items we did choose. So arrange everything, divide out the number of ways that you can arrange the items you didn't choose, and then also divide out the number of ways you can arrange the items you did choose. And that's what you get. So let's do an example. So that would be like if you have 14 fruits to choose from, how many different fruit salads could you make if each uses 5 fruits? I know the plural of fruit is fruit, but when you're talking about multiple kinds of fruit, then the plural becomes fruits. So, yeah. So this is combinations of 14 objects taken 5 at a time. So you don't care like what order you put the fruit in because you're going to mix them all up. Okay, this is a combinations thing. So that is 14 factorial divided by 14 minus 5, that's 9 factorial, and also divided by 5 factorial. And what I like to do in my calculator is I do 14 factorial divided by 9 factorial, and then divided again by 5 factorial. And we get 2002. 2002. And yep, I have one more example that I jotted down, but it's a permutations example, and I already did a couple of permutations. So that should do it for this lesson. Now, I will say this about this chapter in general. A little bit with this lesson, but more so in some of the lessons later on. The challenge is not the math in and of itself. The challenge is figuring out or deciding which flavor of the math to use. And that's where please just check with me if you're not certain, because there's a lot that just comes with experience of identifying, okay, so based on what's happening here, here's how we need to calculate this. So again, yeah, the challenge is not calculating, the challenge is not solving, the challenge is deciding or figuring out which kind of a scenario you are dealing with. And again, some of that comes with experience, and some of that experience comes in the form of checking with me. So you can send me an email, you can shoot a comment on Google Classroom, be like, Mr. French, I think that this question is a combinations thing. Is that correct? Or like later might be like, Mr. French, I think this is a conditional probability. Is that correct? And yeah, feel free to check and check frequently, and I will help you out to help make sure that you're doing it the right way. Okay, that's it for now.